Hello everyone and welcome back to PC Retro Programmer. Today's video is a standalone video and doesn't belong in any of our series, but it follows on from a question that came up in the most recent video in our Advanced CGA Graphics series. There we've been trying to develop some cycle accurate graphics effects for the IBM PC with a CGA graphics card. And one of the things you have to do there is get the machine completely silent so there are no interruptions to mess up the cycle accurate timing. And one of the biggest sources of these interruptions is dynamic RAM refresh. This is a process where the machine goes through all of the system RAM every couple of milliseconds and re-energizes it so it doesn't lose its contents. And this is done via the DMA controller off a timer which is in the programmable interval timer chip. Now one way you can stop this interruption is just to turn dynamic RAM refresh off, but of course that means your memory contents are going to decay over time. And we expected that maybe we'd be able to take these chips outside their spec by maybe a couple of milliseconds, make them delays twice as long or 4 times as long before we did the dynamic RAM refresh, before we'd start to notice problems. But when I did some simple experiments, I was getting times of a couple of seconds, more like 1,000 times out of spec. And so this led to a lot of really interesting questions on the channel itself and also via other communication channels. And since then, we've done a little bit of work to try and understand this issue a little bit better. And so today's video is really just to update on that specific question, which is a really quite general question for the IBM PC. How often do you have to do dynamic RAM refresh? So that's what today's video is going to be all about. The first thing that I want to do is bring up the data sheet for the actual memory chips that I have in my IBM XT. So I have an original IBM machine with an IBM main board, the 256 kilobyte XT board, and it's actually been upgraded to a full 640 kilobytes. Now this is relevant because the idea that I had in the previous video is that we'd just keep the first bank of RAM alive. Basically we'd use an old version of PC-DOS that doesn't use very much memory, and we'd write a very small graphics program so that everything fits in that first bank. And then that's the only memory that we'd need to keep alive. All the rest of the chips in the machine can just be left to decay. And when we're finished with our program, we'll zero those all out, and that will correct any potential parity errors that might occur. We'll turn dynamic RAM refresh back on, and the machine will be none the wiser. But in order to make that work, we need to know how big that first bank of RAM is. First of all, we're going to need to fit everything inside that, and secondly, that's the amount of memory that we need to keep updated. But when I made the previous video, people started saying if you have an XT with 640 kilobytes of memory in it, if you've got the 256 kilobyte board, that first bank is not 64 kilobytes, it's 256 kilobytes. So I decided to check into this, and indeed there is a document from IBM, a little mod if you like, that explains how to upgrade the machine from 256 kilobytes to 640. And the way that you do it is to take the 64 kilobit chips out of the lower banks, put them into the upper banks, and then put 256 kilobit chips in the lower banks. And this is not what's happened in my machine. I checked this very carefully. Bank 0 is labelled very clearly on the board, and the chips in that are these 64 kilobit chips. Now this just shouldn't work, but it does. I checked that there is actually 640 kilobytes of memory in the machine. I put data in each 64 kilobyte block and different data in each one, then went back and read the contents again to make sure that it's all still there, and it is. The machine's working perfectly, it's just not set up the way that IBM said. And this is very unusual. I see no evidence on the top of the board at least of any wires or cuts that were done to make this work. It could be something under the board, I haven't pulled it out and checked, but clearly there's a different mod other than the one that IBM recommended that makes this work. And I have no idea how common this is either, but from the comments on the video, not very common at all. So this has some consequences. It means that I can't write my code to just keep the first 64 kilobytes of memory alive. I have to keep at least the first 256 kilobytes alive, otherwise it won't work on other people's machines. But at any rate, the chips that I have in that first bank are definitely these 64 kilobit ones. 8 of them together make 64 kilobytes, and there's one extra chip for parity. And so the chips that I have in my machine specifically are these Samsung KM4164 chips, and this is the data sheet for those here. Now it turns out that this data sheet has some very interesting information which I missed the first time that I read it. You can see it says that it has a 2 millisecond refresh time. And this confused me because all the other information that I've read elsewhere says that for this size of chip it should be 4 millisecond, not 2. And I looked at this 128 cycle here and didn't really know what this meant, and concluded that this must be a rate at which you have to refresh the chip. But that's not what's going on at all, so let me explain. So internally, this is what the chip looks like. You can see it has a big array of memory cells. It's a 64 kilobit chip, so there are 65,536 of these. I think that's a little typo there. And it's laid out in 256 rows and 256 columns. And so the way that you would access memory cell is that you'd first specify a row from 0 to 255 with this 8-bit address bus here, and then you'd specify a column using the same pins, and that would give you the specific bit that you wanted to access. And it turns out that in order to do refresh, you don't need to access every single one of the memory cells, you just need to access every single one of the rows. And so that means that you only need to access 256 rows to do dynamic RAM refresh. And it actually says later in the document that this chip actually has 256 rows. And so when I looked at this, it really didn't make any sense at all. What does the 128 cycle refer to, and why is it 2 millisecond? Well, it turns out that a lot of early machines couldn't do a 256 row refresh. They were expecting a 128 row refresh. This was very common. And so when memory manufacturers made chips, a lot of them would use this 128 cycle refresh. So basically, even though there were physically 256 rows, you only needed to refresh 128 of them, and the other 128 would be refreshed for free. And you had to do it every 2 milliseconds, and this was compatible with these other machines that were expecting this 128 cycle refresh. But on a PC, where you'd go through 256 rows every 4 milliseconds, basically that would just do the refresh twice, and so you'd have 128 cycle 2 millisecond refresh. So it was a trick to make it work on machines like a PC and at the same time on these other earlier machines. Now it turns out that someone's documented all this, and there's a really nice website which I'll show you now about the various memory manufacturers and what they did. So this is the -0degrees.net website, which is an absolutely fantastic resource for information about early IBM PC hardware. And basically on this page here, they have a list of all of the memory chips that they could get their hands on. There's a lot more than what I'm going to show in the video, and there's a link in the description if you want to check out the actual website. The important thing for us is that they actually list which ones are 128 cycle 2 millisecond and which are 256 cycle 4 millisecond chips. And you can see, and it's the case all the way down, that the 128 cycle 2 millisecond configuration is actually much more common than this other one. And this is presumably because this gave the manufacturers the maximum compatibility with all the different machines that these chips could be put in. So I thought that was really interesting information, and so now we know exactly what we have to do to refresh these particular chips. But of course, it could well be that someone has the 256 cycle 4 millisecond chips, so we need to be a little bit careful about that. Now, there's a few really interesting questions that we could try to answer in today's video. The first is the obvious one. Exactly how long does it take before we start losing memory contents? Is it really just a few milliseconds, or is it more like seconds? And an easy way to find that out, at least for the chips that I have, is just to write a little bit of code and test it directly. So that's what I've gone ahead and done. But there are some other interesting questions we can try and answer at the same time. One of those questions is there any difference between the 64 kilobit and 256 kilobit chips? Maybe as technology improved, the chip quality went up and the decay time is actually longer. But it could equally go the other way around. It could be that there's a die shrink involved and the little cells got smaller and they leak more rapidly, and so actually the decay times are shorter. So this is something we'll try and check in the video. And the third thing that we should be able to check, which has really fascinated me, has to do with the way DRAM works. My naive idea was that every time you do a read or a DRAM refresh, it just sort of charges the value up a little bit and gets it a little bit closer to the value that it's supposed to be. But it turns out, after talking to a few people about this and looking into how the technology works, that this is probably completely wrong. It seems that when you read DRAM, it's a completely destructive process. The value is completely lost. And the way the chips work is that when a read happens, the value that's read out is then amplified, actually really quite a lot, by sense amplifiers, and rewritten immediately back into the cell to replace the corrupted value. Now you can see that there's no way that you could do this in a half-hearted way. Because the value's already been completely corrupted by the read process itself, you really have to fully write that value back in immediately after, and so that's what the chips do. So the upshot of this is that there's probably not going to be any difference between, say, DRAM refresh every 5 milliseconds and DRAM refresh every 50 milliseconds. And actually, if the chips really take a second to lose their contents, then you could even do it every 500 milliseconds and still get away with it. It's just not going to make any difference. So that's something that we'll try and look into as well today. Now, unfortunately, there are questions that I can't answer. I'd really like to have a nice graph showing a statistical distribution of how many bits fail very quickly and how many take a long time to fail, and just plot that. You can get that sort of thing for very modern chips. Intel produced these, for example. But unfortunately, on these old machines, it takes so long for DRAM to actually decay that to test this for a whole load of bits in the machine would actually take a really long time. So it's probably a little bit outside the scope of today's video, but if any of you guys want to come up with an idea and write some code to check that, I'd be really interested to see the results. Now, there's one other thing I want to mention, and it has to do with a question that came up in the previous video. Someone asked, what happens if the values in a byte of RAM all decay to 0, and we will try and check today that that's actually what happens, and the parity bit decays to 0 as well. That wouldn't give a parity error because 0 is the correct parity value for a byte with all zeros in the bits. So will this even detect a complete decay? Now, it turns out the XT designers thought of this, and Re-Enigni kindly looked at the schematic and checked that the parity bit is actually inverted in the XT. So even if the little cell decays to a 0 in the parity bit, that will be interpreted as a 1, which would be the wrong parity value for a byte of all zeros. And so it actually will detect a catastrophic failure of the refresh mechanism. Now, as someone pointed out in the video, parity checking is a pretty bad way of checking for errors. In modern chips, they have much more sophisticated techniques For example, there's error checking and correction, ECC RAM, which can actually correct errors when it finds them. And if you're running a computation on a large supercomputer, for example, which I have done in the past, you have to check whether or not it has this kind of RAM or not. Some do, some don't. And if they don't, you have to build stuff into your code to detect these single bit errors if it matters, because you will get quite a few of them over a very large computation, and we've actually measured this. But if you have ECC RAM, you won't detect any errors at all. It would be very, very unlikely that you get errors that will fool the ECC mechanism, and this is what we found when we ran some very large computations on a supercomputer. So the modern technology is way better than parity in these very old machines. Let's take a look at the little program I wrote, decay.asm, which you can find at the link in the description. Now, you will have to modify this if you've got a 256 kilobyte bank instead of a 64 kilobyte one, but I'll show you the address where you do that a little bit further down. If you want to build this program, you'll need Turbo Assembler TASM version 2.0, and it's just TASM decay to assemble it, and T-link decay to link it into an executable that you can run. So very easy to build. Now this program is going to run through 11 times, and this is just so we can see if there's any variation in behavior. And it's a very simple idea. Essentially what we're going to do is keep the first 64K block of memory alive. That's where DOS and our program reside. And we're going to test the second 64K block. Now, basically what we're going to do is write some values into a block of memory, wait some time with DRAM refresh turned off, and then read the values back and see if any errors occurred. And as I said, the whole program is going to do that 11 times. Now, the delay is set by this value here. This is the number of milliseconds, and the last time I ran this program, I had a delay of 6.6 seconds, as you can see. It's also very approximate, by the way. I didn't bother trying to get this precise. So we're actually going to be putting all ones into memory. So we're going to set all the bits to 1, and then we'll read that back, and we're assuming that the values are going to decay from 1 to 0. So that's something we'll be able to test here. And I'm only going to check a block of 256 bytes. The reason for that is I want to count the number of bytes that had errors within a single 8-bit register. And in addition to that, the program would actually be really slow if I made this number much higher. So this was pretty much the limit of what I could do. If you want to write something a little bit better, please do and let me know. So then we have an array here. Every time the program runs through, each of those 11 times, it will store the number of errors that were detected. Now the first piece of code is just a routine for printing hexadecimal values. I'll skip over that. And the main program starts down here. And the first thing we do is turn off dynamic RAM refresh and also disable the non-maskable interrupt. This is the interrupt that fires when a parity error occurs. And remember that we're deliberately allowing memory to decay here and then reading it back to see if it's changed. That would normally trigger a parity error and halt the machine. And we don't want that to happen, so we have to disable the non-maskable interrupt. Now, every resource I looked at, including books, had the wrong code for this. It didn't work on my XT, so this is the code that actually worked for me on my machine. The next thing that we do is to write those 256 bytes that we're testing in that second bank, and we're going to set them all to binary ones. So I'm going to assume that they're going to be decaying from 1 to 0. And this second bank on my machine starts at address 1000. If you've got a machine with a 256 kilobyte bank as the first bank, you would need to make this 4000. So that's a change that you have to make to run it on a normal XT. The next piece of code that runs is a loop to read back the values. and to count the number of errors. Now, this is going to run immediately the first time, and this is just to check that the program is working. Because it runs immediately, there should be no errors, and so the first value that it should record is 0 errors. But then there'll be a delay of 6.6 seconds the next time it runs, and then we should actually start to see some errors accumulating. So you can see this code is pretty straightforward. It just checks all the values to see how many of them are still FF, and it just counts up the number that are not and puts that into the AH register. Now the next piece of code is actually optional, and I've got it commented out at the moment. With this code uncommented, basically what it does is write FFs back into that block of memory, so resets all the bits back to all ones. And so that means that you can run the same code 11 times starting from all ones and see if there's any variation in behavior from run to run. With the code commented out like it is here, it's a little bit different. What it's going to do is run 6.6 seconds. If any of the bytes decay, it just leaves them decayed, runs another 6.6 seconds and sees if any of the other bytes decay. Now remember that every time we read, that's doing a memory refresh, so it could be that none of the other bytes ever decay. So this will be an interesting test to see whether it's just random which bits decay or whether it's always the same ones. The next piece of code basically just records the number of errors that we counted. We stored it in the AH register, just puts that into our array of errors. So we should end up with 11 values, and the first one should be 0 errors. Then finally we need to have a delay, and I just set it up so that at the top of this delay loop there's a delay of about 1 millisecond, and we just run this loop however many times you want. So in my case it was 6,600 to give me a total delay of 6.6 seconds. Now it can't just do a delay, otherwise the memory where the program is stored is also going to decay, so we actually have to refresh that memory manually. That first 64K block is refreshed by this little piece of code here, and I explained how this works in the previous video. Basically we just have to access each of the 256 rows in that first bank. So once we've run out of delay, basically we just loop around to the start again and run the program again. And as I said, it'll run through 11 times. Once that's done, we're basically going to turn DRAM refresh back on, zero out all the memory that could have decayed, and go back to DOS. Now, one little surprising thing is I had the idea that I should probably re-enable the non-maskable interrupt before going back to DOS, but if I did that, I always get a parity error. It seems that if a parity error occurs while the NMI is turned off, it isn't reset somehow. So as soon as you re-enable the NMI, at least on my machine, it seems to trigger a parity error. So in order to stop that happening, I had to leave the NMI off when going back to DOS. Anyway, that's how the program works, so let's run this and see what happens. So here's the absolutely crazy results of running this program. I actually ran it through twice just to check, and each time it ran for a total of 100 seconds. So the first value you see is after 0 times, so there are 0 errors, and then every number you see after that, an additional 10 seconds has passed. And as you can see, in each case, only one byte out of the 256 has an error in it. And because I'm not resetting these errors, that means that none of the other bytes failed in any of those 10-second intervals, which is insane. It really means that these Samsung chips, at least, run way outside of spec. Now, the other thing I should mention is when I ran this the other day, I was getting errors creeping in at about the 6.6 second mark, whereas today it was more like 10. And I think the difference is temperature. I started the machine from cold today, whereas the other day it had been running for quite a while. Now, this could actually explain why these chips have to run so far out of spec. If the number of errors was, say, quadratic or even exponential in the temperature, then at the top range of what these chips are designed to run at, you might actually get errors much more quickly. So that's one potential explanation. Another explanation, of course, is that whilst in general the silicon was very good, it's impossible to control it perfectly all the way across the chip, and that there are some regions on the chip where you get failures much more quickly. And so in order to shield against that, they really have to have a very good overall process so that these occasional bits of bad silicon don't make that much difference. So that's another potential explanation. It's not something we can easily check today. We've answered two of our questions. How long do you have to wait for errors? Well, a hell of a long time. And the second question, if we do refresh at an interval that's way outside of spec, do things just progressively get worse over time? And as you can see, the answer is no. When that refresh occurs, it fully rewrites the value, and it's not as if it's just recharging the cells a little bit each time. It really fully does that. So the only question remaining that we can answer today is, what's the difference with the 256 kilobyte chips? So I'm going to run that now just by changing the address to a bank that uses those, and we'll see what the difference is. Well, here's the result of running the program with the 256 kilobit chips. So first of all, I changed the address from 1000 hex to 2000 hex. This is the third bank in my machine, which is where the 256 kilobit chips are. By the way, if you modify that address, it's the first 3 times you see 1000 hex in the program. Just ignore the others. So when I ran it the first time with a 10-second delay, I got 0 errors whatsoever. 20 seconds, same thing, 0 errors whatsoever. This is running it with a 40-second delay, and here you can see that virtually all of the bytes had an error in it. Not quite all, but nearly all. Actually, the first time it ran there, you can see we got 6F hexadecimal errors, and then that went up to 7.3 in the next run. But basically, it's roughly the same in each case. So this is a really surprising result. It means that these chips can run a huge number of times out of spec. Probably a couple of thousand times out of spec. And certainly these 256 kilobit chips don't seem to be any less reliable. If anything, they're more reliable than the 64 kilobit chips. So that answers our other question. Now, I think it'd be a little bit irresponsible to finish off the video leaving the impression that you could write code that was hundreds of times or even thousands of times out of spec and still have it run on everybody's machine. Almost certainly that's not the case. In fact, I doubt that it's even the case on my machine. There will be occasional bits, no doubt, that really have very short decay times. And probably there are chips that are borderline that might not even meet the spec. This is old technology we're dealing with. It's very possible that some of the chips have started to fail in one way or another. So I don't expect that it's a good idea to write code that is very far out of spec, but I think it's probably safe to do it a few times out of spec. What I'm saying is that if you're doing the memory refresh at least once every frame, probably that's going to work on most machines. Of course, you have to face the reality that it might not work on all machines. And as we've seen, there are some complications such as whether or not it's a 64K bank or a 256K bank, and whether it's 128 cycle or 256 cycle refresh, and so on. But once we bear all of that in mind, I think that we can come up with a strategy that works in most cases and should lead to some really cool effects. If you'd like to check that out, well, of course, I'm going to have some future videos on exactly that on the channel.